Hello, this is Mr. Miller and welcome to video 4G. This is our second video on related rates problems. And this time we're going to focus on some tricky cone problems. We're going to do 4 examples, so hopefully after that they're not so tricky anymore. Here's our first problem. Sand is pouring from a pipe at a rate of 16 cubic feet per second. The falling sand forms a conical pile on the ground. The height of the pile is always 1/2 of the radius. How fast is the height changing at the instant when it equals 4 feet? So when the pile is 4 feet high, how fast is the height changing? Well, we have a pile of sand here and it does kind of look like a cone. So let's see if we can figure this out. So we're going to start with the relationship or the volume formula for a cone. Volume equals 1/3 pi times r squared h. Now, R, H, and V are all changing with respect to time, and we're going to find a relationship between their rates. But this problem really only talks about volume and height. I mean, it wants to know how fast the height is changing. So they end up giving us a second relationship here that we're going to use also. They say the height of the pile is always 1/2 of the radius. So height equals 1/2 r. Or if I multiply both sides by 2, I have 2h equals r. I can take this and substitute it into the formula for r, and then I only have v and h. It's a way of getting a formula for just volume in terms of height. Okay, that's why this problem is tricky. All 4 problems have this kind of feature. So if I do that, I get volume equals 1/3 pi. Instead of r squared, we have 2h squared times h. So instead of r, we have 2h squared, then times this h. So 2 squared is 4. I can write this as volume equals 4/3 pi. I have h squared here and another one, h cubed. Okay, so that's what was tricky is I got a formula for the volume in terms of h alone. Okay, now we're going to take a derivative with respect to time. So dv dt equals 4/3 pi times 3h squared dh dt. Remember, we need the general power rule. H is a function of time. So 3 times h to the 1 less power times the dh dt. Now, the 3's cancel here. So I have dv dt equals 4 pi h squared dh dt. Okay, now it's time to plug in things we have. Sand is falling at 16 cubic feet per second. That's how much the volume of the pile is changing. Cubic feet is a unit of volume, so this is 16. 4 pi, and we want to know how fast the height is changing when it's 4 feet high. So this would be 4 squared dh dt. Okay, now if we solve for dh dt, we would get dh dt equals 16 divided by 4 times 4 squared is 64 pi, which is actually simplifies to 1/4 pi. Okay, and if you wanted to actually calculate this, that'd be about 0.0796 feet per second. That's how fast the pile is growing. Not that fast, right? Okay, wow. That was a lot of great math. Let's do it again. So here's another kind of sand pile problem. There's another big pile of sand in a parking lot. It says sand is pouring from a pipe at a rate of 22.5 cubic feet per second. The falling sand forms a conical pile on the ground. Sounds familiar. The height of the pile is always 2/3 the diameter of the base. So there's a relationship between h and r. Find the rate the height is changing at the instant the height is 6 feet. We can do this. So it's going to follow the same pattern. We have volume equals 1/3 pi r squared h. Then we have the second relationship, that h is 2/3 of the diameter. Remember, the diameter is twice the radius, so instead of d I can put 2r. So it means that h is 4/3 r. Now, if I multiply both sides of this by 3/4, I get 3/4 h equals r. And that's what I can substitute in here. So we get volume equals 1/3 pi times 3/4 h squared times h. Or volume equals, this is going to end up being 3/16 pi h cubed. Now we take a derivative. So dv dt equals 3 times 3/16, that's 9/16 pi h squared dh dt. Okay, let's add what we know. dv dt is 22.5 and equals 9/16 pi times h squared, h is 6, so 6 squared times dh dt. Okay, so we get dh dt equals, it'd be 22.5 times 16 divided by 9 pi times 36. Okay, and when you do all of that, you should end up with, I got 0.354 feet per second. There we go. So that's how fast the height is changing. Okay. This one is another cone problem. It's slightly different. This time water is filling up a kind of a cone-shaped tank. So overall, the tank is 12 feet high and has a radius 4 feet. The water has radius r and height r. I'm sorry, height h. Okay, so we're going to start with the same thing. They want to say that water is pouring into it at a rate of 8 cubic feet per minute. Find the change in the depth, which is h, the height. So it's kind of a similar problem. So volume equals 1/3 pi r squared h. Now, just like all the other problems, we need a relationship between r and h. This time we're going to get it from similar triangles. See this triangle I'm kind of shading here? This triangle right here is similar to this bigger triangle here. So the side that's length r matches the side that's 4. So r over 4 equals h, that's this side over here, over 12. Okay, so remember, matching sides of similar triangles are proportional. R over 4 equals h over 12. Okay, that gives us a relationship. If I multiply both sides by 4, we get r equals 4/12 h, which is 1/3 h. Okay, that's what we're going to substitute into the formula. So we get volume equals 1/3 pi times 1/3 h squared times another h, or volume is 1/27 pi h cubed. Okay, derivative time, dv dt equals 3 over 27 pi h squared dh dt. Okay, so, well, water is being poured in at a rate of 8 cubic feet per minute, so that's a change in volume. So that's 8. 3 over 27 is simply 1/9. Pi, h is 6 again, so 6 squared dh dt. Okay, if we solve for dh dt, we get dh dt equals, it'd be 8 times 9 divided by pi times 36, which ends up being 2 over pi. And 2 divided by pi is about 0.637, and this would be feet per minute, since those were the units for this problem. Well, we're up to our last example. Okay, so again, we have a conical tank, radius 1 meter and height 12 meters. Water is pouring in at a rate of 2 cubic meters per minute. Find the rate of change in the depth of the water when the water is 5 meters deep. Okay, here it goes again. Volume equals 1/3 pi r squared h. But there's a relationship between r and h. So this triangle here is similar to this triangle right here. So r over 1 equals h, that's this side here, over 12, which is the length of that side there. So r equals h over 12. Well, we can plug that into here. So we get volume equals 1/3 pi h over 12 squared times h, which is 1 over 3 times 12 squared pi times h cubed. All right, so dv dt equals 3 times this. The 3's will cancel, so we just get 1 over 12 squared pi h squared dh dt. Again, plug in what we know. So dv dt is 2. That's how fast the water is pouring in. This is 1 over 144 pi. H is 5, so 5 squared would be 25 dh dt. So we get dh dt equals, well, it'll be 2 times 144 divided by 25 pi. And if you do that on a calculator, that works out to be about 0.147, and this would be meters per minute. Okay, so we did it. Now, these are really complicated problems, but we see they all follow the same pattern. All right, time for you to give it a try. So we have a conical tank. So this is like the last two examples. It has radius 8 feet and is 12 feet high. You can see the similar triangles right here. It's kind of this little blue right triangle and this bigger triangle right there. So you know that r over 8 has to equal h over 12. Anyway, water is pouring into it at a rate of 9 cubic feet per minute. So I kind of broke down the problem a little bit. Use similar triangles to find the relationship between r and h. Write the volume formula of the cone so it only has h in it. And then take the derivative and find the rate of change of the height of the water at the instant the height equals 4 feet. Okay, good luck with that.